Okay, good morning. We will continue today's class from where we left in the last class. Of course, in the last class, because of some network issue, I was unable to complete the portion what I was intended to teach you all. Anyhow, no problem. We will cover up that in today's class. And we are currently learning lateral dynamics part. We have done sufficient number of classroom learning for response of the vehicle bicycle model is concerned. And we just have started our lecture after our CAT 2 examination to understand in detail what do you mean by stability of your vehicle or stability analysis of your vehicle. So when I say stability analysis of vehicle, we have also seen that as we introduced to the lateral dynamics, the vehicle would have two kinds of unstable state, especially on the ground vehicle. That can be one is unstable state that can happen for a vehicle in a plane itself, yaw plane itself, that is on the ground surface itself. Another unstable state can be the rollover problem of your vehicle. That vehicle would go out of the road, it will topple, it will in the sideways. So that is what is called a rollover unstable state. So these are the two aspects that we are going to learn. Maybe we are going to look at them mathematically, and then we will start with the other two important modules of our course. Which is longitudinal dynamics and tire mechanics, where we will be learning some important tire models. So that's what is the current status and the plan for the remaining part of our semester. So in today's particular class, I have two objectives. One is I would like to explain you how can you write nth order system governing equation, which is of ordinary differential equation of nth order. How can you represent that as a state space form? The state space form is not new to you. We were able to get our state space equation for our bicycle model straight away. So what is the advantage of state space model is if I have nth order system, I can represent that as an n single order system. N single order system. So that is going to help in many ways to tackle, understand the solution of your differential equation, or further to see how can you have a control system designed for your vehicle so that you are going to have a required dynamics only for your vehicle. That what do you mean by required dynamics only for your vehicle is it has to undergo the expected motion, not the not getting into an unstable state. So such thing is our objective. The state space representation and the state matrix is very good one, so that we would be able to have control system design and so on. So I'm not going to teach you entire automotive control system, but we are just going to have two steps, two important aspects, representation in state space form, and to understand a simplified stability criterion called Rao stability criterion. So these are the two things I would be teaching in this particular course. And that would excite you to go through a textbook that I have told in the last class, Modern Control Engineering by K. Ogata. So you can look at that book and it would be very nice, and every chapters are nicely explained, and there are MATLAB functions, codes are written, so it's easy for you to follow and strengthen yourself, and that would be an additional enhancement along with this vehicle dynamics course, right? So with that brief note, let me just share my screen to start today's class. So this lecture number 33. And today's date is 12/11/2021. So first, let us look at how can we represent an ordinary differential equation that governs a system into a state space form. So for that, I'm just going to take a simple equation of second order equation that is very much we are familiar with our spring mass system. So I'm just going to take single degree freedom spring mass system, spring mass damper system. Okay, and this is C. I'm going to look at the input given to this is say U of t, and the response I'm going to have is Y of t. If that is so, I know my governing equation can be obtained by applying Newton's second law from its static equilibrium position. So if this is its static equilibrium position, and we have done that all in first module, I'm just taking that equation, that is my double dot plus cy dot plus ky equals v of t, right? So this is the governing equation. So this governing equation is what I want to represent as a state space form. Right? So how do I do so? So for that, let us just define the following. So I know my output is y. So that let y equals q of 1 or y equals q1, right? And then I have its differential y dot equals, that is q1 dot, that's equal q2. Then let me write y double dot equals, just a minute, there is some distraction outside, some sound. Yeah, y double dot equals, I can write this as q2 dot, right? Q1 double dot is equal to q2 dot. So by defining this, I am able to now convert this differential equation of second order into state space form. That's what we are going to see now. So let me write from this equation 1, y double dot would be, so I divide this equation by m and then write for y double dot. So that's going to be minus c y dot by m minus k y by m plus u of t by m, right? So this is y double dot. So what is y double dot? Y double dot is q2 dot. So this is my q2 dot is what is y double dot. What is that on this side I have? So I can rewrite this as like this, c by m y dot minus ky by m plus v of t by m. So this is my equation, say 2. So what is my equation 1? Equation 1 is this equation. Q1 dot is equal to Q2 is what is my equation 1. So you would immediately make out now Q1 dot and Q2 dot. So these are the derivative of the state variable. And I can rewrite now this equation 1 and 2 in this form, where I have my Q1 dot, Q2 dot vector on left hand side. On my right hand side, I will have now a matrix. I will have first row of the matrix 0, 1. Why first row of the matrix 0, 1? This matrix is going to be multiplied by Q1, Q2 vector. So what are this vector? Q1, Q2 are my state variable. So Q1 dot is equal to Q2 is what we have it. Plus I will have E of t. So here I will have 0. So now you see first row represent my equation number 1. So now I would know what is my second row. So Q2 dot is what is from a second equation. If I look at, I can rewrite this. I can rewrite this equation 2 again in a convenient form. This is Q2 double dot. That's equal to, what is y dot? Y dot is Q2. So that's going to be minus c by m Q2 minus k by m y. What is y? q1. So minus k by m q1 plus u of t by m. So this is my second equation. So the second equation when I plug in here inside, so that's going to be, now look at q2 double dot, right? So it's not q2 double dot. This is q2 dot, which is y double dot, right? So look at this. So q2 dot equals, I have to get this equation. So q2 coefficient is this, that is going to be here sitting. So that's going to be minus c by m here. And q1 coefficient is minus k by m, that's going to be here minus k by m. So you see now second row, q2 dot is equal to minus k by m q1, that's there here, minus c by m q2, that's there here, and plus this. So it should be here 1 by m into this. So this is 1 by m. So like that, if I write, now look at this, is what is my state space form. Of a differential equation represented. So in this, what has happened? My second order ordinary differential equation, non-homogeneous equation, because I have an input on the right hand side, is now represented by two single order equations. So this is what is the advantage? Yes. So in this similar fashion, I can write my nth order system equation into n single order equation, and that's what in the generic form we have written. So I can rewrite this as what? Q vector, Q dot vector, which is the derivative of state variable, and that is given by this matrix. Now is 2 by 2 in this case, is going to be my A matrix, which is called the state matrix. In general case, it is going to be n by n, and this is going to be in general case n by 1, and into Q, which is n by 1, plus here this is B, which is again n by 1 E of t. So this is my state equation, where it is one single input, and then you have it's not here it is not multiple input multiple output problem. It is one single output, that is q1, and you have an input only with one input. So it's single input single output condition, you get like this representation of your state equation. And of course your output equation, so this is state equation called, and your output equation is very simple to write. Output is what? Your y. So what is y? Is q1. So I have to write this y equals, I will have 1 0. So this is a row vector into q1 q2. So this is what is my output equation. So it is y is equal to q1 is what is my output equation. That's what first we have written. So this equation here is what is output equation. So when I give an input u of t, I'll get an output q1. So the state variable q1 is what is output of this system, single output system. So single input here is u of t is what is single input. So here this input function can be an impulse function, direct delta function, or a step input function, or ramp function, like that. So in a single degree of freedom vibration model, mass damper, spring mass damper, you are able to get your output by providing an input by this. So this is a representation of your equation only. It is not the solution. It is not a solution. It's a representation of the equation. So one governing equation, we are very much familiar with vibration basics. My double dot plus cy dot plus ky equals u of t can be represented now in this new understanding form called the state space form, right? So if this happens to be for an nth order system, how do I generalize my equation? So that's going to be written like that, you would see in the textbooks. So Q dot, if I don't put parenthesis also, it is understood, it is Q dot A into Q, where Q is your state variable, plus BU. So this is your generic form state equation. And your output equation Y would be equal to C matrix times Q plus D matrix times U. That's your output equation. So this is for multiple input, multiple output LTI causal system. So please look at the textbook Ugata and get to know with this what do you mean by linear time invariant causal system, linear time invariant non-causal system, non-linear time invariant causal system, or non-linear time varying causal system. Like that you can have many, but what is that we are going to look at in our vehicle dynamics at this course is linear time invariant system. That's what we are going to. And it's a causal system. Causal system means it is not going to be futuristic. Non-causal system means it depends upon the future parameter modification and so on. Non-causal system means it is going to every value depends upon what is the past definition of your parameters. Right, so you can look at the definitions of individual, what is linear system, non-linear system, causal system, non-causal system, time varying system, all. That's all simple to follow. You can please read the textbook. At the moment, I'm just writing down these equations in this. If you look at here, this equations order, let us see this matrix, the size of this, since it is for nth order system I'm writing, this A matrix here is what is called a state matrix. And the size of the matrix is n cross n. So if it is nth order system, it is. So bicycle model is second order system. So we get A matrix 2 by 2. Right? So you have your vehicle to be as a single degree freedom model system. If we have that, would have your system to be of 2 by 2 matrix, state matrix. So B is what is called an input matrix. And if it is multiple input, then you will have here M cross N. Because we looked at that generic equation on left hand side, you looked at the equation of nth order differential equation, and the right hand side mth order differential, ordinary differential equation. So that comes, if you represent that, the B would be not a vector, it would be matrix of this size in a generic case. And C is going to be output matrix, and that is of the order P by P. So there are P outputs. So we say second order system, but output is only one. So the P can be less than N. So, but multiple outputs. So N is the nth order, and P would be less than N or equal to N. And D matrix is what is called in this is direct transmission, direct transmission matrix, that is given by order M into P, the size. So M you can see here, since it is associated with straightaway input. So if I have some input and direct transition matrices, that input can be straightaway influenced by some parameter. Then it has to act on an input, and that would be straightaway having an influence on the output. Most of the cases, this direct transition matrix would be 0, like we have seen in second order system. Or it is there, it has to be accounted. So this is how you are going to represent your nth order system for its multiple inputs, and then the expected multiple outputs by state space equation and its output equation, right? So what is the advantage of having written this equation? So we have looked at in a control system design, I require something called G of S, which we call it as closed loop transfer function. So if we have to get this closed loop transfer function, that is going to be written as y of s by u of s, right? So you would have here a polynomial, numerator polynomial and denominator polynomial. In denominator polynomial is what is called a characteristic polynomial. So in the last class we have written, so the order of this characteristic polynomial is n. Order of the polynomial in numerator is m. So if m is less than n, then it is called strictly perfect transfer function. Like that all we have defined. So what is important here is this denominator polynomial is what is describing the characteristic of your system. So nth order polynomial equation is what is defining nth order system characteristics. So when I make that is equal to 0, I make a condition that I look at my system without an input. I just look at my system with this initial condition and giving some disturbance. And that kind of analysis is what is called an eigenvalue analysis. That is essential for our stability analysis, right? Remember that point. So now let us continue with this representation of equations. And what is the advantage of A? So you see here, you see here this determination of transfer function is obtained through this ratios of two polynomials, or you can also represent. So these two polynomials, how does it come? You are left hand side and right hand side ordinary differential equation, you are taking Laplace transform with the initial condition 0, and you are able to represent into polynomials. And then to find out the roots of this polynomial, denominator polynomial, you are required to go for partial fraction technique. And that's going to be sometime very complex even to be handled by MATLAB if there are some parameters that are deciding your characteristic of the system. So in such cases, to get your roots of this characteristic polynomial for an eigenvalue analysis problem, can be skipped if you go for a method proposed by Raoult's stability criterion, that we will see in a while. So just let me finish this part of discussion by representing how can I get my transfer function g of s from this matrices A, B, C, D. If I have my nth order system, I represent by state space form. How do I get g of s? Let us just look at that. And for that, if you have here the state equation, I take Laplace transform on both sides of the state equation with 0 initial condition. My first equation, state equation, would be written as this way. So what is that? It's going to be S Q of S minus Q of 0. So why Q of 0? This is initial condition 0. So you have your first order differential, you will Laplace transform on first order differential would be this S Q of S minus Q of 0, that is equal to, on the other side I have A matrix times Q of S plus B U of S. And my output equation y equals, so that is going to be y of t in time domain Laplace transform when I take with 0 initial condition is going to be y of s equals c into q of s plus d into u of s. So now what is that I'm going to do is this. Let's look at this. I would have to have this Q of s on one side, and this is, so this equation would be written again as S Q of s, and this is going to be minus A into Q of s, and that's equal to B U of s. Right, so here this Q of s, if I take, it is all our matrices, so this S Q of s when I take, it's going to be S times an identity matrix of the size of A minus A into Q of s, that's equal to B E of s. Right, so in this, what is Q of s now? Since it is matrix on one side, this, if I take it on the other side, that's going to be inverse. Si minus A inverse B E of S. So now I have this Q of S. This Q of S can be substituted in this output equation. So let me substitute that in this. So that's going to be Y of S equals C into Si minus A inverse B E of S plus D E of S. So if I take E of S out in this, it's going to be C into Si minus A inverse B plus D into U of S. So this is Y of S. So what is my closed loop transfer function now? That is Y of S by U of S. So I would have my G of S would be Y of S by U of S. And that's going to be C into Si minus A inverse into B plus D. So this is how I can get my transfer function of the system by having A, B, C and D matrices of multiple input, multiple output case, right? So even it is for single input, single output, you can use this where you will have your sizes accordingly. And D would happen to be most of the time 0 or it is known, then you can include that. So this is how you get your G of S. If you have your differential form of governing equation of nth order into state space equation, n number of single order equations and the corresponding output equation, you would be able to get this. Right, so writing this form has got many ready functions in MATLAB so that you define this A, B, C, D of your system. It will solve for your state variables and then it become very simplified. So the examples of MATLAB functions and codes are available in Modern Control Engineering by textbook Ogata. Please go through the textbook and you'll have some idea. May not be, I'm not going to diverge from our focus of vehicle dynamics. For exam point of view, may not be having more of control system, but you can't just say that no, I don't want to study more control system. It is important. That's why I just want to have particularly this lectures to have that insights also to have some idea, right? So this is one thing of having a state space representation, advantage of finding transfer function through state matrix, output matrix, input matrix and direct transmission matrices. So now let's get into looking at what is the raw stability criterion, right? So that's my second objective of today's lecture. Raw stability criterion. Okay, so I would also, before coming to this, I would also represent, before getting into this, I'd like to represent this. So let's go to that. What is that? Is the representation of the state space equations what we had into control system block diagram. So if you are representing as a block diagram, that helps you to design or looking at parameters that are important explicitly in your system. So for that, let me just draw a block diagram representation of the equations what we have derived, what we have represented here. So these are the state equations. And how do I represent this state equation in a block diagram? So that you can connect this equation nicely to develop a block diagram that can be further reduced to a convenient form to design control strategies, right? So for that, let me write what is that is block diagram of the linear continuous time control system. When it is represented in a state space form, how do I write it? So that's very simple. I have my input. Input is what? B into U. So I have to get that. So my U is E of t. My input is a function of time. That is why continuous time, linear continuous time control system. So E of t, and that would be passed through my input parameters B. If this input parameter B is constant, then it is time invariant system. If this input parameter B matrix also is function of time, then it is the continuous time control system. So let us take a generic case B of t, and then I have this input sent through a summing point. In control system design, you will see this summing point, branch points, and so on. And finally, this to represent our equation, right? So I have this. This is plus. So this getting added at this junction, and I will have another addition to come here. And before that, let's look at the output of this is going to be my derivative of state variable q of t. So in my equation, q dot of t equals a q plus bu, right, is what I'm writing. So this is my output here. So B of U, BU is there here that comes. So what is to come here is AQ to come here. That should get added. So that's very clear. So here I have to get parameter A of t. So time varying, and just representing the parameters inside A matrix also is function of time. But in our bicycle model, you see them, they are not. For a steady state condition, they are not, they are constant parameters. So A matrix would be a constant matrix, right? Then it is time invariant system. So if I have this A of t coming here, these two addition is what is my state equation. When I say here A of t into Q, I have to get Q, not Q dot. So what I have to do from Q dot, how do I get Q? I should have a function here which is an integrator. An integrator, if I pass through this, I would get an output here is Q of t. So this is forming the system parameter. So this Q of t is passed through this, and then it is taken here. So I have these two, and equal to this first equation is represented. So the state equation is represented in a block diagram like this. Right, and then I have here this Q of t is what is my output. So that is C of t, and then I just take it out. What is my output equation? Y is equal to C Q plus du, right? So now this is my Y. If I have to say this is my Y, I should have here again a summing point. Why summing point? That this term is coming. There is two terms here, so summing point. So I would have that like this. I have here plus, and there is one summing point. So here whatever that I have, Q of t is nothing but Y. So this two multiplied is what is this first term, and I have to get du. So du, how do I get? From here. So it's u input. From there I will get this, and this is my d of t. And that doesn't have any anything undergoing in this process. It's straight away going to be influence added with my output. That's why it's called a direct transmission matrix. So here, so I get my output y of t. So this is what is that simple representation of your state equation. So this is the state equation 1 and the associated output equation. These two equation is represented now in a block diagram for linear continuous time control system. So in these all blocks, B of t, A of t, D of t, or C of t all are constants, then it is time invariant system, right? So you understand here this Q of t, when I say that's going to be function of Q, U, and T. So it's function of state variable, function of your input and time. And y of t is also is a function of q u t, right? If these vector functions, these are called vector function here, functions do not involve time t. In this, they do not involve time t. If this q dot of t is function of only q and u of t is only this, then that is called a time invariant system, right? So remember that. So if this is so, it is simple now for a second order system of our equation. What we had can be represented. So what I have to do for that? So this is my u. I do not have d. D is 0 in that. So u, and u is multiplied with what? B. So what is B in my second order spring damper mass system? It's 1 by m. So I get this, and then goes to a summing point, and in the summing point I have here addition, and I'm going to have here, instead of addition, subtraction. Why subtraction? You'll understand now, right? So what is the output of this? This output should be q2 dot, and I send this through an integrator. I'll get q2. So where q2 is q1 dot that we have seen, and then again I'll have to have another integrator c, and I'll get q1. So q1 is my y. Q1 is my y. So now my equation is what? Here I have my right hand side. So your equation is this equation. You have to look at it. This equation you have to look at it. You have to look at this second equation. Q2 dot equals this. So I had to get Q2 times this. So that can be. So this is there straight away now. I had to get these two terms. For that two terms, I require two more blocks. So that would be brought in here. So I will take out from here and send that through. A block contains a parameter value c by m, and that I take it here, and I take here again a summing point, and that's plus, and this is also plus, and from here I'll take another one, and this one will be k by m. I take this to this. So here I have c by m q1 dot k by m q1, both are added, and that gets into this. So where here it is subtraction. So I will have my equation q2 dot is that, right? So q2 dot is what now? Here whatever that I have is my equation. So q2 dot is that comes from here. That is c by m into q1 dot, that's q2, minus k by m into q1 plus this term u by m, right, is what is my second equation. And q1 is equal to y is what is my first equation. So the two equations are represented now in this block diagram. So this block diagram does not have direct transmission matrix. So in this, what are my A, B, C, D? In this case, it is simple. So what is my A? State matrix is 0, 1, minus k by m, minus c by m. What is my B? It is not a matrix, it is a vector in this case, column vector 0, 1 by m. What is my C? Output matrix. In this case, it is a row matrix, it's 1, 0. And D is 0. So by having this all, I would be able to get my transfer function for the system. Or these parameters can be used in a control system design. Okay, so this is all something, when you look at the control system, when you say you should be able to represent, and that to modern control system means you should be able to convert a differential form of governing equation of the system into state space form, where the number of single order systems would be there. If it is a fifth order system, you'll have 5 single order state variables, right? That's what is in mind. And then you are able to represent those state space equation into a block diagram. And there's something called a block reduction technique, and then you can reduce this block diagram into simple one in this way what we were representing. This can be represented as an input, and you will have here G of S, and you will have your output Y of S, and this can be taken as here. So I can reduce this all simply like this. So that's something block reduction technique and so on. We are not taking many of the physical example and to put it in this, except the known vibration single degree freedom model only I have taken here. There are chapters only in the textbook Ogata to have different physical system and how do you represent the control equation, governing equation, then equivalent block diagrams and so on. So that itself is a subject and course. Okay, so now let's get into this Rao stability criterion. So what does this criterion state is without solving for the roots of a characteristic equation, I would be able to comment on an absolute stability of the system. That's what is the statement of Rao stability criterion. So what I mean is what is now I'm going to write the equation and then let us see. So we have looked at our G of S as B naught S power M plus B1 S power M minus 1 plus B2 S power M minus 2 plus and so on plus B M minus 1 S plus Bm divided by A naught S power N plus A1 S power N minus 1 plus A2 S power N minus 2 plus and so on plus A N minus 1 S plus AN, right? So this form also we were looking at the ratio of two polynomials. So in this denominator polynomial is what is called a characteristic polynomial. Characteristic polynomial. So let me take that. So what will happen for stability analysis? For stability analysis, this one. For stability analysis, you have to use what is called an eigen value. That's otherwise called eigenvalue analysis. So eigenvalue problem solving. So eigenvalue problem solving is your input is 0. So my state equation Q dot equals A into Q plus BU. So that's equal to 0. So Q dot is equal to AQ is only equation that I should consider as B U equals 0. So there is no input, right? That's equal to 0. So if I do that, so what will happen? I have this is obtained how I have on one side my nth order differential equation, on the other side nth order differential equation. Nth order differential equation goes to 0. So I'll have my characteristic polynomial equal to 0 is what is I would get. So that I can also represent here if I put my Q of S as a trial solution as Q into e raised to st and substitute and do so, I would end up with writing this polynomial a naught s power n plus a1 s power n minus 1 plus a2 s power n minus 2 plus and so on plus a n minus 1 s plus a n equals 0. So then this is called the characteristic equation. We don't call this as characteristic polynomial. This is called characteristic equation. So we have studied that the roots of these equations called the poles. The roots of these equation is called poles. So if there is nth order polynomial equation, I'll have n roots, and that n roots would be represented in my complex plane, that is S plane, where I have real part on x-axis and imaginary part j omega to minus j omega. This is my S plane. So if my all these n roots are lying on left half plane, then the system is stable. If all the roots are lying on the right half plane, this is called right half plane. Right half plane. If some of the roots are lying on the right side, that means what? The roots will be positive roots, or the roots are complex conjugate roots and with the positive real part, then it would be lying on this. So if I say my roots are lying on horizontal axis, what do I say? The roots are real roots. The real roots can be positive roots or negative roots. So negative real roots are stable system. If roots are lying on vertical axis, what do I say? The roots are complex conjugate roots. And if that is lying on vertical axis, the system is stable, but it will be oscillating. It will be vibrating. The oscillation is present in the system. If the roots are lying on right half plane, I call the roots are complex conjugate roots, complex roots with the real part positive. And such roots are there present in your system. The system is unstable. If any one root is present in right half plane, then system is unstable. So this is what is that you should understand. So if I have to investigate that whether the system is stable or unstable, I have to find the roots of this equation. So finding these roots of this equation for nth order is not a simple task. We know that the roots can be obtained by partially factorizing this nth order polynomial into linear roots or linear and quadratic fractions. So I can have s plus a as a root and s squared plus bs plus c as a quadratic root. So I can factorize this polynomial, nth order polynomial, into number of linear factor and quadratic factors. So the linear factor would give me s plus a is a root, then s is equal to minus a. So that would be on the left half plane. So this is minus a. If I have here s squared plus bs plus c, I would have, since the b and c are positive, I'll have here complex conjugate, complex roots. So with the negative part, that will also fall on this side. So having nth order equation and factorizing them as linear and quadratic form necessitate here a condition that the terms here a, b and c's all should be positive. That's important. This all should be positive. If in this, if I have negative, minus b is negative, then I will have a real part of my complex root. So to ensure that the roots all of this are lying on left half plane, I should have this a, b, c of my factors of my linear or quadratic factors should all be positive, right? So that's the condition. So that way, if you look at this polynomial is involving some parameter of your system, and that system would get imposed to have a particular value or a range of values, when that would ensure these values are positive. So that is how it will go. But here the question comes as, how do I find the nth order system roots? That's going to be, factorizing is going to be complex. In such cases, can I have an answer to tell about the stability without solving for the roots? Yes, that's what is proposed by Raoult stability criterion. So Rao stability criterion state that I can immediately tell, looking at my characteristic equation in the stability analysis without factorizing them. How? All these coefficients of this A0, A1, A2 up to AN all should be positive. All AN, A0, A1, correct, comma, A2 and so on up to AN, all should be greater than 0 value. That's an important condition. If that is so, I can say that the roots are positive. The roots are going to lie. Roots are going to lie on the left half plane. I would have my roots lying on the left half plane. Whether they are real roots or complex roots, that we do not know. But the important condition is, if I have these all coefficients positive, then I would be able to state the absolute stability of the system. That's what is proposed by Raoult stability criterion called. But that is not sufficient. That's a necessary condition, but not sufficient to comment on the relative stability of the system is coming into picture. So if I look at here, one of the term is negative or one of the term is missing here. That means what? One of the coefficient is 0. Then also I can comment immediately the system is unstable. If one of the term here is negative, I can straight away look at this and say the system is unstable. Absolute stability is concerned. But the question is, if it is found absolute unstable, can it be possible to convert into a stable system? So if that is so, what are the conditions that should be imposed? So if that is so, it is necessary but not sufficient that what are the sufficient addition or modification can be brought in the system. That's what is proposed by Raoult stability criterion. The limitation of this condition is that it will be suitable for linear time invariant system alone, and you would see that the relative stability is concerned. This method is not that viable, and you have to do some modification in your S-plane by shifting your axis of S-plane to another place, and looking at an equation once again by replacing S by S minus sigma substitution, and then you would be able to comment. So you can make this method viable without solving for the roots and commenting on the stability of the system. That's what is this Raoult stability criterion. So what I will do, we will look at in the next class again this Raoult stability criterion with some example problems, and then look at our bicycle model. Already we have done that. So if you are imposing now this Raoult stability criterion on bicycle model, looking at your state matrix, you would be able to arrive at the condition that for the stable system of your vehicle. So of course we require another half an hour. We will do that in Monday's class, and then we will get into rollover stability analysis. And once that is over, we will be completing almost 80% of the syllabus, and then remaining part we will learn systematically. With that note, I will stop today's class. I would recommend that you please go through the textbook Ogata, browse through the chapters and this topic all. It is very simple to follow the textbook, right? Good day to all of you. If you have any doubts, you can ask. Otherwise, I'll end the lecture at this moment. Downloaded your attendance. Stop sharing. Recording.